chemical reactions and so on. So the multiphase flow, this will include fluid flow where we have multiple different phases that have different properties. So we'll have, conceptually, we can have mixtures of gas, liquids, and solids, or potentially also multiple liquids that are immiscible. So within that overview, we can think about it in two ways. We can have discrete phases. So we've got two different phases. They've got different properties, and there's an interface between them, and that's what's that is basically defining the important processes. We can also, though, have two phases that are intermixed, okay? And so you can have two separate phases that are together, let's see, like this. So we could have here's oil and water, right? So there's an oil droplet in water. So that would be this case. But then, and really this, you could visualize this as a matter of scale. We could have a mixture where there were many oil droplets, for example, or many droplets of some separate phase in there. And we don't want to treat each one individually. We want to treat this as a mixture that has its own set of properties. Okay, so those will be the two approaches. And let's just see a couple of examples of what we're talking about here. So here's small scale, two distinct fluid phases. And so here's the picture of oil droplets in water. And these are, I guess, really, it's also some oil and water. And in this case, what we have are two liquids that are immiscible. And at this small scale, we see they form these round droplets. What's important there is the surface tension along the contact between these two fluids. That's what's forming it into these circular patterns. So at small scale, we've got this picture here, and there's here's a little droplet of, well, this is water and oil now, and there are forces between the two liquids here, and then between the water and the solid that will control the dynamics of the water and oil and solid mixture. Okay, so that'll be surface tension between the two fluids, and just generally interfacial tension that's going to be important at these scales. So we can also look at this problem of oil and water, two immiscible fluids at a somewhat larger scale. A couple years ago, when I was teaching this class, there was the Deepwater Horizon disaster that happened, and that was in the news. So these pictures were current. But basically, problem of we have oil droplets, individual droplets floating in water, but then we can have a whole much larger body of oil. And this is an example of that done in some experiments where there's this leak and this accumulating low-density fluid floating on top of the water. And you can see at larger scale, they're forming some interesting patterns. This is maybe, I don't know, this is probably, it looks like this is say 100-meter scale, something like that. And then at an even larger scale, certainly could be interested in how this oil moves around floating on the water. And here's an example of I think this is actually a simulation of the distribution of the oil and how it moves around. So certainly a problem of two different immiscible fluids at a wide range of scales, from millimeter scales for the droplets up here to many hundreds of kilometers. So we can have similar things for fluids or for material that is it's not oil. This is an example. We've got people in the department who are working on algae for biofuels and for other purposes. And so algae, some algae anyway, grows as these kind of mats of I don't know, clumps of stuff that floats and forms essentially something like an immiscible phase, much like oil, but with different properties. So that might be another example of two fluids that we might be interested in. So the density of the fluids, that's going to be an important. We saw surface tension at these small scales. Density will be important for these two immiscible fluids. Here's an example of two fluids that have a density contrast, and this is an experiment where this fluid A is lighter than fluid B, and it's injected. This is shown in cross-section, and we've got this kind of characteristic shape where the fluid A is along the bottom here. That's what's called, it's grounded there, and then it has this interface. Looking down on it, we've got a nice circular pattern that's shown here. When the type of the fluid that is injected is changed, we go from this kind of a pattern where this fluid was injected right here and spread out, and you get this nice uniform pattern. This would be a stable displacement of the light fluid by the dense fluid by the light fluid. And then if you change the fluid, and probably what's happening here is the viscosity is reduced, and you have a situation where you inject, and now you have this unstable pattern where the fluid, instead of spreading out as a nice uniform front, it's coming out in these fingers. Okay, so this is an example of unstable displacement, still of a light fluid displacing a denser fluid, but when you change the viscosity contrast, you go from a stable over here to unstable. You can see another example of that. Here's where you have what we just saw was fluids that were basically the light fluid is on top of the dense fluid, and that's a stable configuration where you can just have the light fluid floating. But in this case, a dense fluid is introduced over top of a light fluid, and in that case, that's unstable. The dense fluid wants to be on the bottom. And so this problem is basically looking at how does the dense fluid go from up here on the top to down here on the bottom. And what happens is it forms this really kind of interesting pattern. As this is also a problem of, or an example of an unstable displacement where what's happening is this dense fluid is moving down by these individual little fingers that are descending, and they drop down, and then you can see they have these little balls at the end. So this is a kind of a characteristic pattern where the dense fluid is displacing the less dense fluid in this with these unstable fingers. And here's another example of that. I mean, this one is pretty familiar. It's in a wine glass. This is, I think, just some dyed fluid. Here's some stiffer fluids that are done in a centrifuge under high G, and you can see this is we've got a similar. And in some ways, it's kind of similar because we've got the fluid penetrating down like that. This fluid is moving up, but you have the penetration goes by this kind of finger that then has kind of a wide head to it, And so it comes down and the flow kind of goes like that. And this one is doing the same kind of thing. And you have this very regular spacing along it. Okay, so that's an example of unstable flow of two immiscible fluids. And here it's driven by density. The instability, as it turns out, this tendency for the fluids to penetrate as these fingers is, you don't need a density contrast to do that. You can do that with just a viscosity contrast. And here's an example where a low density fluid is injected into a high density fluid in a Healy-Shaw cell. So this is a flat plate, horizontal plate, with a sheet of probably glass, transparent sheet over top of it, and fluid is injected right here. The low density or the low viscosity fluid is injected right here, and it spreads out radially. And so because it's low viscosity displacing high viscosity, that's unstable, and you have this effect where you have these fingers form as the displacement occurs. Okay, here's another example of multiphase flow. This is in flow in a pipe, and we've had a couple of examples in class of flow in pipes, so some simulations that you guys have done. Those were single phase flows in laminar conditions and then also in turbulent conditions. If you introduce a second phase, so if you have, say, a flow of liquid and you introduce a gas, then you can have lots of different things going on. And conceptually what happens, it will really depend on the ratio of the gas to the liquid. And here's some experiments that were done in a small tube where the flow could be photographed. And you get these different, I guess there are 10 different regimes that are recognized here that depend on the ratio of the liquid to gas. So at small amounts of gas, you have this one here, that's where it starts. So they're just putting a small amount of gas in, and they have what's called a bubbly flow. And then as you increase the ratio of gas to liquid, the bubbles become larger and go from these roughly circular shape to these more shapes that, well, they're spanning the diameter of the tube, and they have this characteristic shape where they're kind of flat on the bottom and then more rounded on the top. And then once they reach the side, then they can the bubbles can kind of move as a piston through the tube. And so this is now a larger bubble there, and this is a slug flow because you're having pockets of gas and pockets of slugs, kind of a region where it's almost all gas, and then a region where it's almost all liquid, progressing along. Okay, so the style of the flow has changed dramatically just by increasing the gas content. And so there are a couple of different types of slug flow, and then you increase the gas even more, and you have the gas forming more or less a continuous conduit, and the liquid is now along the sides, and that goes on. And then I guess here's more annular flow where it's really just confined to the sides. Okay, so very broad range of characteristics. I don't know. Everybody's seen this, right? When you drink through a straw, right? It starts out just all over here, all liquid, and then when you start to get down to the bottom, I don't know, and it starts making the slurping noise, you're probably doing some slug flow there. And then at the end, when you want to get the last little bit, you've got turn flow and annular flow, and you're just getting down there. So this is, I don't know, it's pretty diverse, interesting set of physical behavior. It also will raise some challenges if we want to go ahead and simulate this kind of thing. Okay, so we also have, when we're thinking about unstable flows, We've got those examples that are fairly low viscosity fluids, liquids, but we can also turn to the geologic record and see some features that are much larger. What I'm showing here are these are geophysical cross sections of what's called a salt dipier or salt dome, and these are examples of features where you've got a layer of salt here, like that, overlying or overlain by sediments that are denser than the salt. So this is unstable. You've got the sediments at this large scale behave like a fluid, and so you've got dense over light, and that's unstable, and so it starts to forming into a wavy pattern, and then these guys grow like so, and form these dipiers. And you can see that in some cases anyway, they grow and then they have this kind of enlarged head, like is shown here and to some extent here. So these are probably, I don't know, hundreds of meters across, maybe a kilometer across, and a couple of kilometers high. So they can be quite large features in the subsurface, and that's another example of density contrasts. Okay, so we've seen a variety of different processes, and I think it's worthwhile to look at the different properties that are controlling this. So here are two fluids, fluid 1 and fluid 2, and they have different densities and different viscosities. And so one of the things that will be important is to be able to track the interface between these fluids. When we're interested in small-scale processes, the interface is going to be really a critical thing. So if we look at that interface here, when we track it, we can think of a couple of things that are going to need to happen. One is that as the interface moves, we don't want to have any gaps form. Conceptually, there won't be gaps forming, or there won't be really anything, the fluids penetrating, kind of overlapping. So to that end, the velocity in this fluid at the boundary and the velocity in that fluid at the boundary have to match. So that'll be one of the requirements. And then we also have to be able to balance the forces across the interface between the fluids. So to do that, if there's, in just kind of a simplistic way, the force balance would require that the pressures on either side of the fluids are equal. But between two fluids, we also will have surface tension, and that surface tension will result in forces. And so basically what this amounts to is that the net force that will be created by the pressure and the surface tension have to balance out. Okay, so that'll be a requirement for our analysis. So the surface tension is going to be important. The size of the problem will be important. We saw viscosity and the density, and the velocity. Here I called it u, and here it's v. So these are going to be some of the important properties. Now, one convenient way to think about this is to take these different properties and combine them in dimensionless numbers. So we did that a couple of classes ago when we first started looking at laminar flow. We introduced the Reynolds number, which was the ratio of inertial forces to viscous forces, and it was really saying how important basically the inertial forces that we get from velocity are relative to the force which would, I think, tend to promote turbulence, for example. How important those are relative to the viscous forces from viscosity that tend to damp out the flow. And so Here's the Reynolds number. And now that we've introduced the surface tension and density, or in particular density and gravity, we saw gravity was going to be play an important role, then we'll have other ratios of things. And here we show how surface tension is playing into it. So this is the Weber number here, this one. And it's the ratio of the inertial forces to surface tension forces. So, well, let's go through all these. So this is capillary, the capillary number, and this is the bond number. And in all cases, we've got these different forces. For the Reynolds number, we've got inertial and viscous, and so for Weber and capillary, we just take those forces and scale them to the capillary forces. And then for the bond number, we introduce the buoyancy force and scale it to the surface tension. Okay? So what you see from this is the surface tension, well, for the Weber number, for inertia, as the velocity increases, the inertia becomes more important. That makes sense. But also we see this length term in there. So if we hold the velocity constant and the surface tension constant, just increasing the size of the problem increases the Weber number, and it makes inertia more important than surface tension. And down here with the bond number, we see that we've got the size of the problem with characteristic length to squared. So what that means is that, well, here rho g, that's going to be the unit weight of the water, and that'll be, or the unit weight of the fluid, so that's going to be governing the buoyancy forces. But we have L squared in there, so as the size of the problem gets bigger, this number gets bigger, and increasing the size would have the same effect as increasing the unit weight or decreasing surface tension. So one of the things that happens with this, at least in these two cases, for the Weber and the bond number, is that what we expect is that small problems will behave differently than large problems with respect to surface tension. The small problem surface tension will be important. As the size increases, the importance of surface tension will drop off. Okay, so one thing too that this has brought up that I think would be worth mentioning is the effect of, well, we saw buoyancy, that was important. We're having these two fluids with contrasting density. The buoyancy effect obviously is going to play an important role. And even if we don't have two fluids, we just have one fluid, then just the hydrostatic pressure within the fluid, that would be something that would be of interest. And we haven't really shown yet how to include that. With the problems that we did for our homework, I think we really were just interested in the pressure drop, and we didn't really have any kind of a buoyancy effect. So let me show you where that is and how we'll include that. So what I've got here is the momentum conservation, the Navier-Stokes equation, and for momentum conservation. And these are the terms. We did this a couple of times already. And so this is the convective acceleration. This is just the acceleration from velocity changing with time. This is the term with the stresses. And then this is what will end up being the body forces. Okay? So right now, we don't really see how hydrostatic pressure is included in this. So let me show you. Let's do a problem where it's only going to depend on hydrostatic, right? So we'll have here a column of fluid that is got a free surface there, And let's see, so that's the height of the free surface, and that'll be z upwards. And we're really just interested in the vertical effect. So it's just hydrostatic. We want to get the pressure distribution in this, right? So it'll just be linear pressure distribution, but we want to get it out of here. So what we'll say is, for this problem, the velocity equals 0. And I see here that guy that says v, but that should be u. That's the velocity there. So our problem here, our hydrostatic problem, is that the velocity is 0, and if that's the case, then the change in the velocity with time is also equal to 0. So it's just sitting there. And if it's 0 everywhere, then the divergence is going to be equal to 0. Okay, so for our problem here, we can go back up here to the Navier-Stokes, and this guy, just 0, right? So that's 0. The acceleration of velocity, that's 0. These are the strain rates, and so they'll be 0. That's how the velocity changes spatially, right? So they're 0. And so all we end up with remaining is that, and that. So what that gives us is this. So del, this would be minus the p is a scalar, so we just, when this guy is applied to that, we just get the gradient of p. And actually, let me just do it like this. So all of this stuff here, that's just equal to 0. And then we have equals minus del p plus f. Okay? So that's what we get for Navier-Stokes simplified for this problem. Now, we said that it was 1D, right? So del p is going to just be dp dz, right? And let's bring it over to the left side so we get that. Okay, so the pressure gradient is just, so I guess what we see here, F, we said F was just like it's a source. This comes from the source of momentum, but we never really did anything with it yet. But what we see here is that it's the vertical pressure gradient. And that will be minus g times the density. So g is gravity, the fluid density. The minus sign is because z is up, and we want this to act in the downwards direction. Okay? Or we can also write it just minus gamma, minus the unit weight of the fluid. So we can integrate that. We integrate that. We get p minus gamma z plus the constant of integration. And we'll say that the pressure is equal to 0 at z equals h, right? So then what you get, you solve for the constant, you just get this guy, p equals gamma times h minus z. H minus z is just going to be the depth. Okay? So this is what we expect for the hydrostatic pressure. It just is going to increase with depth. Okay, but the important thing here is that we start with this, which is the equation that we're starting with in our simulations, and we see that if we want to include hydrostatic pressure, if we want to include buoyancy, that kind of thing, then it's here in this body force. That's how we do it. And the the magnitude of it is here, the unit weight of the fluid. Oops. Unit weight of the fluid, and we have to specify what direction it's acting in, and that's where that minus sign is. Okay, so we have to specify all of this stuff. If you want it, I don't know, if you want to do this on the moon, then G would change. If you want to do it upside down, then minus would change. If you wanted to actually, some of you are working on this project where we're interested in what happens to a column that's laid over on its side, and so that flow is induced there. Well, what happens, the way you do that is you just change you change basically the direction in which the body force is applied. Here, this is doing it in the minus z direction, but we can change that. We can have it go in plus z, or we can have it have other components. Okay, and so if you want to take a body and lay it over on its side, rather than actually physically moving it in the simulation, you just change the direction of gravity. It's a lot simpler. Okay, so that's how we'll include gravity, buoyancy, body force as a body force. Now, there are going to be several different kinds of multiphase flows that we'll want to be able to simulate, and we've seen some examples of them so far. At the top is just multiple fluids, and here's this example of oil floating on water, and in this case, we'll have fluid 1 and fluid 2. They'll be separated, and there'll be an interface between them. Okay, so that'll be one type of problem that we'll want to deal with. A special case of that is where you have something like this, where you have a liquid and a gas. Okay, so there are two fluids, different properties, and we might be interested in what's happening there. Now, we might want to treat that as two fluids, but there are a lot of different problems where we don't really care too much about what's happening with the gas. And so the pressure in the gas has a lot lower viscosity than the liquid. The pressure in the gas stays pretty much constant. When the liquid flows, the gas, we're not really interested in what the gas is doing. So we just we treat that as, we just forget about what's happening with the gas. And what we're interested in, though, is the surface of this liquid. So that's a free surface problem. Here's an example of that with this droplet falling on the surface of the water. So if we're interested in what the surface of the water is doing, sloshing around, forming waves, those kinds of things, then we can treat it as, we can think of it initially as this multiple fluid problem, but then we forget about the gas to simplify it, and then we can treat that. And there are a couple of ways of doing that. So then there's another type of problem where we've got two different phases or multiple phases, but they're intermixed on a very small scale. So we have particles of one fluid, or particles of a solid, or particles of a gas in another liquid. And so here's an example of that, where we've got a sediment-laden fluid, like a slurry, that's in water. And so that's a variety of applications for that, and that's going to be clearly a different scenario than these guys. One of the ways to think about that is that this fluid here, the fluid that has multiple phases in it, we can think of that just as a separate fluid that has some properties that are affected by the two fluids that are in it, or the two materials that are in it. So if we have a a fluid that consists of a lot of gas bubbles, then we could think of it as two fluids, but we could also think of it as one fluid that has properties that depend on the ratio of the liquid to the gas. And then also we have the multiphase flow problem in porous media, where the porous media is saturated with, porous media contains multiple different phases, water and air, for example, or perhaps different Napple phases. In this case, the properties also will vary, and they're going to vary with the saturation. They'll vary with the concentration of the different fluids. Okay, so those are different types of problems, and this will give us several different types of simulation methods. So for the multiple fluids, we're going to have to deal with two fluids with an interface between them. And there'll be two main ways that we'll look at to deal with this. One is called a level set method, or a phase field method. And this will allow us to, this introduces a new variable that is used to help basically track the interface between the two fluids. So this level set method, it's done on just we have a problem domain, we put in our mesh, and we solve it, and we have these two fluids moving across the mesh. Another approach is to start off with two fluids that we identify, and we identify the interface between them, and then we move that interface and we move the whole mesh with the fluid. Okay, so that'll be another approach. It uses a technique called alternating Lagrange-Euler, or ALE, moving mesh, and these each will have some advantages and disadvantages. Now, for the free surface problem, we can use these same techniques, level set, phase field methods, where we just basically put in gas for one of the fluids, and there'll be some advantages to that. One of the disadvantages is that it's pretty computationally intensive to do that. So if we want to really focus our energy on one fairly small region, then this will work out nicely. But if we wanted to do a big region that has this free surface, like the ocean, then we might want to think about other approaches. And one approach that has been developed is to recognize that a lot of flows are much bigger laterally than depth-wise, a lot of free surface problems, like in the ocean or the atmosphere. A lot of water bodies are shallow relative to their lateral dimensions. And so what you can do is take the Navier-Stokes equations and simplify them to account for that. And so you're then including that free surface without having to deal with what the air is doing. And actually you're simplifying the overall problem. You're making it into, if you wanted to analyze the flow in the oceans, for example, you would think of it as really a 3D problem, but with this approach, you're averaging over the depth and you reduce it to just a 2D problem, okay? So it simplifies it down, it makes it a lot more tractable. And those equations are called the shallow water equations. So they would be part of this free surface analysis. So for many small discrete particles, then there are a couple of different methods, a variety of them actually, that analyze the mixture of these particles and fluid, either like gas bubbles in a liquid, liquid bubbles in a gas, like a spray, solid particles in a liquid, like a slurry. One of the tricks with these is that, well, on one hand, you have to have the property of that mixture, but the other thing that's tricky is that you have to be able to analyze the transfer of momentum from the particles to the fluid, right? So it's not just a matter of the properties changing. as you have these particles, you drop a bunch of sand in water, then as those particles are descending, that's going to cause the water to move. So there's coupling of momentum there. So there are these mixture models. Then we can also, though, just use particle tracking. So you guys have been you did some particle tracking already, right? Those particles were just like tracking particles. They didn't really, they weren't particles per se, they were just to watch how the fluids are moving. One of the things we could do, though, is introduce mass, for example, for the particles, so that they would tend to sink, they would have some inertia, and so we can then track many of them, and that would be one approach to having to doing this kind of a problem. Probably can't track all of them, right? If there are many small particles, but we could track many of them in kind of a representative way. All right, so that'll be another approach. And then there are these porous media problems, and these will involve allowing the fluid saturation to vary, and there are a couple of different ways of doing that. If we're just interested in the water and not really so interested in what the gas is doing, then the Richards equation provides a path forward for that. If we wanted to do both the gas and the liquid, or if we have multiple phase liquids, then we need to go to 2 or 3 phase Darcy approach, and that's possible. We can do all of that. Okay, so those are the options. Quite a big array of stuff that we could do. So what I want to look at first is if we have 2 fluids, and for this we're going to require that we solve for basically mass and momentum are conserved for each one of the phases. So we'll have a Navier-Stokes type equation for each one of the phases. If it's turbulent, we'll have Reynolds stresses. So just like we had for single phase. But then we'll also have the interface between these fluids, and we'll have to deal with that somehow. So these are the options: level set and moving mesh. So here's the level set method. What we're going to do here is we'll have two fluids, let's say. So here's fluid 1. Kind of zoom in here. So here's fluid 1, and here's fluid 2. And so we want to evaluate their dynamics. And one example of this would be a bubble. So fluid 1 could be lower density than fluid 2. And so what we're going to do here is we're going to have to track the interface between these 2 fluids. So the strategy is so basically what we're going to do is say along this interface we have to match the velocities. So we're going to say the normal velocity like that in this fluid. So U1 and U2, the normal velocities have to match so that there are no gaps. And if the problem is small enough and surface tension is important, if the problem is small enough compared to the surface tension, so if like the bond number is small enough, then we'll want to include surface tension as a force that occurs along this interface. Okay, so we're going to have to track the interface, and there are a couple of ways of doing it. We could say, okay, this is the initial position of the interface. We know what the velocity is, and so then we can integrate that and determine what the location of the interface is at the next time step. So that's possible, but as it turns out, that it actually will do that in the next approach, but that's that can be kind of tricky. What's done with this level set method is to say, okay, we're gonna introduce a new variable, phi, and it's going to be a continuous variable that is it's active over the whole region, and this is a plot of phi, and if we look at it in perspective view, that's what we've got here. So phi varies from 0 to 1, and when it equals 1, then that corresponds to the location of fluid 1, and when it equals 0, that's the location of fluid 2, and right here, that's the 0 contour for phi, or no, 0.5. Phi's going from 0 to 1. So this is the 0.5 contour. The contour is a line at equal elevation, so that's kind of level, the level set. Okay, so we have this function phi, the 0.5 contour is defining now the boundary between the two fluids. Okay, so what we have to do is have phi move around, and phi's going to be able to move around in response to the fluid motion, and then it will then feed back, and it will tell the fluid flow problem where the different phases are. Okay, so that's the basic approach. We've got to introduce this new variable, and it's a continuous variable, and what we'll say is that this thing is going to be, it's going to have to behave conservation laws. So that automatically is big thumbs up for us, because we know it has to then obey this conservation, this standard conservation law that we've been working on. So for the level set method, here's the governing equation. So this guy and this guy, these are just standard mass and momentum conservations, and we would have those apply for the two fluids. And then this level set parameter, it also has to behave the conservation equations. So what we get then is we have this change in storage term as just the change of the level set parameter with time, and we have the advection of level set. So basically, this guy phi is what we were in our general approach is the dependent variable is c, so c is equal to phi. So the advection term is just the velocity times phi. So what happens is, up here for the fluid flow problem, we're calculating the velocities, and we let the velocities move this quantity phi around. Okay, so ideally we would just do this. We would have phi changing with time, and it's just moving around with the fluid flow. So the fluid flow goes in this way, and it kind of pushes some of the some phi over there, and that accounts for how the fluids are moving around. The problem with that, though, is if we just have these two terms in here, and I guess in this case s is 0. So if we just have these two terms, just advection and storage change, that ends up being very, very difficult to solve. You get oscillations, it becomes unstable. So what's done is to add in some additional terms to condition the solution, and here I'm writing them here as diffusion terms. So this guy here, there's the gradient in phi. So we said in general, just a diffusive flux is driven by a gradient in our dependent variable. So diffusion of mass is is driven by a gradient in concentration. So now we have diffusion of this level set parameter driven by the gradient, diffusion of this stuff driven by the gradient of this level set parameter. Okay, so that's that guy. This is the width of the transition. So that's right here, this width. And then there's an additional term here, and this also is working as a well, this guy is the gradient, a unit gradient right along this, well, a unit gradient over the whole surface, and then this phi times 1 minus phi. You see this term showing up a lot in these kinds of problems. And so let's see, here's how it works. So let's do a cross section through here. So phi looks like this, and it's 1 here and 0 here. And this is, it's pretty steep right in here, but it's continuous. And then 1 minus phi looks like that. Okay? And so then the product of these two, out here the product is 0 because this is 0, so the product just looks like this. Okay? So the product looks like this. So by using this term here, we end up with something that really only has value right here along the interface. Okay? So this is used to kind of condition and reinitialize the solution, and well, then by substitution we put these guys into our governing equation and we get that. So here's just the first two. That's what we really want to have happen, and then this is to kind of condition the solution. All right, so what we're going to do then is solve this as we go, and this tells us where the interface is going to be. We'll apply the surface tension at the interface, and that's done right in the way that it's implemented in this case is that surface tension is applied as a body force over a relatively narrow band right here at the interface. Okay, so that's the level set method. One of the advantages is that this level set surface, it can get distorted and be quite irregular. It can be kind of rippled in some cases where you might have droplets or separated phases. And so it really gives kind of a nice versatile approach. Here's an example of a droplet coming out of a nozzle, and you can see this it's got its tail and its head here, and then this is a rising bubble that's done with the level set. So these are from simulations. Actually you can run all of these yourself. Let me show you these guys. Let me see. This is the rising bubble. So here you've got it's filled with air, and then there's air up here, and so that's the free surface of the water, and you can see the bubble hits that and oscillates, and you see look at this little jet that shoots up. See that little jet that shoots up out of the center? So that's pretty nice. That's actually a feature that's observed in this kind of a flow. So let me also show you the nozzle. So there's a nozzle, shoots out, and you can see, look up right up there, how the droplet, it it shoots out, it's got a tail, and then the tail breaks up into smaller droplets as it progresses. That's as the surface tension takes a hold and breaks the droplet up into these smaller pieces. Okay, so can get some nice effects from this type of analysis. Okay, so let's see where. There we go. Okay, so here are some examples of free surface flow. We saw that one, I guess. There are a variety of others drawn from surface water hydrology. This is a favorite of mine. I don't know, you guys remember seeing that back in the day where the tsunami went over the seawall at Fukushima. And then here's another pretty amazing photo. This is during Hurricane Katrina. The storm surge is going over one of the seawalls in New Orleans. A dam failure on this river in Iowa, and then a simpler case, but something perhaps easier to visualize on your desktop, is just the water sloshing in a tank. So these are all examples of water with air over it, and here's a similar case from the subsurface where we've got a unconfined water table right there. So interested in analyzing that. There are a variety of ways. The level set method that we just saw is certainly one thing that we could do. I told you about the shallow water equations. Another way to do this is with a moving mesh. And so that's what I want to show you here. So for the moving mesh, what you do is you start out with the region discretized, like I'm showing there. And the upper boundary, we say that the velocity at that upper boundary, or we can do this as the two fluids. Here we're not really including the air explicitly, but we can treat it as two fluids if we want. And basically what we're doing is assigning the boundary condition at that boundary that it's moving according to the velocity of the fluid at the boundary. So you'll see this written as the boundary condition where it's u is the x component of velocity and nx is the x component of the normal vector, and then this is the normal vector, the y component of the normal vector. So that is the normal, the velocity normal to the boundary. Okay, so when the boundary is flat like this, the velocity is just, it gives it that velocity. But you'll see this velocity is changing, or the interface is changing, so the velocity is changing direction. And so what happens here that's really fairly sophisticated is as this boundary moves, as that boundary moves, the entire mesh moves with it. So here's an example. In this case, this is a tank, and the water is draining out of the tank. So you're having flow like this, and the water level drops in the tank. Okay, so if you did this slowly, the water level would just fall like that. Be kind of interesting. But if you do it fast, then you get stuff sloshing around, and it's a lot more interesting then. And so that's what's happening here. You can see this curve to the surface. That's from this wave that's happening as it sloshes back and forth. And so the mesh is being deformed in response to this action, the change in the volume of the fluid in here. And what happens then is these guys get deformed. Eventually, the mesh will get so deformed that it really compromises the accuracy of the solution, and it has to stop. It's possible, though, to set it up so that when that happens, when the mesh gets compromised enough, it stops and then automatically remeshes. So that's one way to extend the duration of these kinds of solutions. So let me show you an example of that. So here it is, where this is where the fluid is flowing out, and just like we open a valve, we got this fluid or this tank filled with water, and we open the valve, and when it replays, you'll see this wave, this big wave, sloshes from right to left. Now it's kind of equilibrating out. This is I think the opening is right to there. So there's the initial pulse, and you get this wave moving across, and then here's this secondary wave. The colors are the pressure, and the arrows are the flow. So kind of cool. Looks about right. And so yeah, this will be one of the examples that we'll do. Okay, so this actually is pretty remarkable. The problem with this rectangular domain, it was meshed, and then this mesh is collapsing, and it's able to run even when it gets down to here. So you can imagine this mesh is very wide and skinny. So one of the problems with that is the accuracy gets diminished. So yeah. Anyway, we'll take a look at that. So that's the ALE method. Okay, so now this other class of problems where we have mixtures of different fluids or fluids and solids, and we want to analyze how that all works. And here's some different examples from engineering. Fluidized bed reactor is something that's used for various processes where you've got some reactive solid particles, and you blow a gas from below up through it, and that causes the particles to become suspended, and you do reactions between the fluid that you're blowing up through it and the particles. And then some various other examples. Here, this is kind of a favorite, where during a volcanic eruption, you've got a big column of ash, gas, and solid particles, very small particles, that gets ejected out of the volcano and forms a column that shoots up into the atmosphere. That is then unstable because the mixture is much denser than the air. So it shoots up out of the volcano, and then it becomes unstable and falls, and then comes down the slope of the volcano like that as a pyroclastic flow. And that's, it makes for some spectacular photographs. It's also one of the big dangers of volcanic eruptions. And then here are some examples of plumes that are formed by liquid droplets or solid particles in air that moves along. And so that would be another example that we might be interested in. I guess we've got a couple other examples. These all look like solid particles in liquids, from hydrothermal vents to density currents flowing in fluids, so a slurry flowing in a body of water, or masses of algae. So that was solid and liquid. If we wanted to do gas and liquid, similar kind of problem. Here we have liquid droplets in a gas, and some kind of a engineering example where we would want to design how this worked. We also have gas bubbles in liquid, where we might want to understand how that works. I mean, probably recognize that. And then we can change the ratio of gas to liquid, and here's a natural example of some liquid particles in a gas, and here's some liquid particles in a gas as well. Kind of nasty, but I thought it was really a great shot, and it illustrates the point here. So, and yeah, actually, then if we go back to this problem of fluid flow in a conduit with bubble flow and annular flow, the thing we're talking about here now is this case and this case. This intermediate case is probably would probably be something somewhat different. So for particle in fluid, there are several ways of doing this. The Euler-Euler method is one where we've got a continuous fluid like water and a dispersed phase like these solid particles. And the volume fraction of the solid particles, it's going to control the density of the resulting mixture and viscosity. And so we're going to want to take that into account. The tricky thing here is to include the transfer of momentum between the particles. There also may be transfer of heat or transfer of mass. You could have the particles dissolving or precipitating, that kind of thing. You could have them participating in a chemical reaction. And the particles could be hot or cold, have a temperature difference compared to the fluids, so we would be interested in how that transfer of mass, heat, or momentum occurs. We also are interested in the interaction. Well, doing this will require that we can include the interaction, the hydrodynamic interaction between the particles and the fluid. So the shape of the particles, their size, whether they coalesce or disperse or break up, all of that is going to play a role and will be something that we would want to include. So here's one of the key things. We want to couple the momentum of the continuous phase, like the fluid and the particle. And what I'm talking about here is that if you have a fluid that's flowing like this and the particle is, say the particle is just neutrally buoyant, then and when the fluid flows, then the particle is going to move. So the momentum of the particle gets inherited, or you have transfer of momentum from the fluid into the particle. And then by the same token, you could have a particle that's dense, you drop it through the fluid, and when that happens, the fluid is gonna flow around the particle, and that will essentially be a transfer of momentum from the particle into the fluid. So we have to include that kind of thing. And we have to be able to do it on kind of a large average scale. So the thing that's introduced here is what's called the slip velocity, which is the difference in the velocity between the difference between the velocity of the particle and the velocity of the fluid, and drag forces between the particles and the fluids. Okay, then we also have to account for the properties of the mixture, the fluid mixture. It's going to depend on the concentration of the solid particles, the dispersed particles there. And the density, usually what you do is you say, well, the density is going to be just kind of you just use simple mixture theory. So you have a certain concentration of particles, certain concentration of fluid, and you can get the resulting effective density there. Viscosity is a little bit trickier. I mean, as we add solid particles to a liquid, if we just put a few particles in there, it's not going to really do much. But as the concentration of the particles gets larger, then you definitely have an interaction between the particles that causes the fluid to thicken. So there are various ways of dealing with that. Here is a simple one where you have the viscosity of the mixture affected, or basically being this baseline viscosity, and then depending on the concentration of the dispersed phase, and then to some power here. Okay, so this would be this is just like an empirical relation that shows how this works. So then we do conservation of mass, And one approach then is to just take conservation of mass on the two different phases. So we've got concentration of, we have conservation of mass for the dispersed phase as well as the continuous phase. That gives us these two mass conservation equations. And then for momentum, there are a variety of ways of, a simple way to think about this is that we have the momentum of the mixture itself. Okay, so momentum is velocity, the momentum per unit volume, we've been treating that as density times velocity. So for this mixture, we've got a density that we just saw. It will depend on the concentration of the, say, the solid particles or whatever particles they are in the liquid times the velocity. Okay, so that gives us a path forward for the storage term for the momentum. This is the advective flux and diffusive flux. All that's just the same as what we've been doing for a continuous fluid. Now we just have this fluid mixture. Okay, so that's simple. The thing, though, that is a little bit tricky here is that we have to have the transfer of momentum between the different phases. So the way that's done is to have a source term here. Here's rho g. That's giving us the density of the, or the unit weight, so that'll give us the pressure, hydrostatics. And then we've got a term here that is the momentum transfer between the particle and the liquid, and that's going to depend on this slip velocity, the difference in the velocity between the fluid and the particles, as well as the mass fraction of the dispersed particles. So just how to do this, variety of ways of dealing with that, okay? But I think conceptually you can see how that's going to be important to handle this process of the interaction between the solids and the particles, the solid and fluids. All right, so I think that's a good, well, actually let's just do this. Just have, well, give me one more minute. We've got a couple of examples. Here's, we can handle multiple fluids with particles, particle tracking, and we also have shallow water equations. So let me show you just the examples of those. So let's see. Here's shallow water equations. So there we hit this protrusion in the flow, and we get these ripples forming. So that's one way to handle the free surface problem. And then we can have multi-phase flow that's handled with particle tracking. So that this is, here's a mixer where we have particles that are injected in from the four sides of the mixer and spin around, and you can see how they're mixed around. So these are particles that have mass, momentum as they spin around, and you can see the effects there. So if you wanted to design a mixer and you wanted to try out some things before you did your experiments, this might be an approach to look at. Okay, very good. See you on Tuesday.